Hello. The title of my EAGE talk is The Unappreciated Importance of Refraction Multiples as Land Seismic Noise. Now, noise is often the big problem with land seismic data. And after about 60 years of land seismic exploration, I argue that we have not identified or appreciated a strong and important type of noise, which I call refraction multiples. Now, people have certainly seen it and often cursed it, but it is not well understood. It hasn't really been given a name. It has not been given much attention, and we don't have good tools to address it. And I hope to change all this. Now, in truth, a variant of this noise has occasionally been called guided waves, and that was by about 30 years ago by Fred Hilterman. But I don't think guided waves is a good term, and it missed some key aspects, and this noise just really hasn't been given much attention. And here's some examples of refraction multiples. On the left is a data set, and you can see here are some echoes of the first arrival. So these are P refraction multiples, and down here are S refraction multiples. They have about twice the travel time as the P refraction multiples. Notice also that the S refraction multiples are a bit stronger than the P refraction multiples, and this is telling, and we'll be getting back to this later. On the right is another data set example. Again, you see the echoes of the early arrival here, and then you see the S refraction multiples here, and then you have some scattering underneath the S refraction multiples. Here are two more data sets. This one on the left is from Papua New Guinea. Here you see a lot of linear events, which are P refraction multiples. And then here we have the S refraction multiples. And you see here a very subtle and weak surface wave. And finally, in West Texas, again, you see these P refraction multiples and then the S refraction multiples here. Now, you may think that a FK transform or a radon filter can remove them, and you partially can, but perhaps with only 50% effectiveness. But these are really strong, and we really want something that has 90 or 95% effectiveness. And these refraction multiples occur around the world. I've been somewhat surprised. They're in Colombia, China, Romania, West Texas, Kazakhstan, Oman, Papua New Guinea, Bolivia, Azerbaijan, Kenya, Egypt, Algeria. There are many places. And they are often the big problem noise. They often cause the no image problem, especially true in foothills area. And I consider them to be the most difficult noise with landmass seismic data, even more difficult than a lot of scattering noise. And truth, scattering noise and refraction multiples often go hand in hand, but there are two really different physical processes. So I think we should call them different names. Now, understanding the refraction multiples points to ways to improve the data. So why have they not been appreciated or recognized before? Well, they actually don't look that difficult. It looks like radon filtering should work well. And they have been called guided waves, which, I don't like. And sometimes they're misinterpreted as surface waves, but they're not. They're faster and they're not dispersive. So refraction multiples actually have subtle complexity and are amazingly strong. And the physics was not well understood. So I think that's why they maybe haven't been appreciated. Also, land seismic issues really don't get much R&D attention, especially compared to marine. And theorists, frankly, don't like land seismic data. It's messy. I think I'm in somewhat of a unique position here as a wave equation geophysicist who likes to get my hands dirty with data, and I see data from many different areas, which is how I recognize this. So let me describe how the physical process behind these, how these are caused. Now we know that greater than 90% of land source energy goes into the surface waves, and often it's 95%. This is pretty well documented, and a key part of this is that the very low S velocity of the very near surface down to 70 or 200 meters per second, that plays a key role. And the very low velocities also cause very short wavelengths on the order of a few meters. And that means a lot of physics happens in the top 10 to 50 meters of the Earth. But the net results, as you can see here, is these surface waves are incredibly strong, and here the traces are clipped by almost by a factor of 10. I mean, this is dramatically stronger than the reflection energy here. Now, in this case, the surface waves stay localized on the near offsets, and you can work with the weaker reflection signal on the middle and far offsets. But what if this strong surface wave energy leaks out? Well, that's exactly the problem with refraction multiples. There's several things that can cause this leakage, and one is just standard layering. So here's a nice example from Andrew Bakulin. It's a 1D model with layering. You can see on these inner offset traces, the surface waves are very strong. They're clipped significantly, but they're leaking out into these faster refractions here. And these faster refractions are in fact stronger than the reflections. This is what has been called guided waves that I think Fred Hilterman defined, but there are other processes that can cause this leakage. And these really are, leaking surface waves. It may be that a velocity inversion in the layering plays a role in this leakage, and I don't think it really matters. Several things cause this leakage. So here again we have the guided waves. They're caused by strong surface waves. But on the right, we have surface wave scattering that's leaking into refraction multiples. And you can actually see the surface wave right here. And it's very weak because it's been scattered in the first few hundred meters, and the scattering has converted it to, well, mostly refraction energy, but also reflection energy that you'll see. And there's also, clearly you can also see some scattering here. Here's a cartoon demonstration of what's happening. And these wavy lines here represent surface waves. Notice the scale here. This is very much the very near surface, 3 to 30 meters, 30 to 100 meters, maybe 200 meters. But a dramatic amount of energy initially gets trapped in this low velocity surface layer, but it hits heterogeneities and then scatters out, and these become secondary sources. You can also have undulations at the bottom of the model that also cause scattering. So several physical processes cause the leakage: layering, undulations, and scattering. Here's a nice movie example of strong surface scattering caused by a sand dune. You can see the sand dune in the middle of the model. This is an oblique view. And we're going to set off a source at the surface. And you can see a lot of energy is trapped in the sand dune, and then the sand dune acts like a secondary source that just radiates for hundreds of milliseconds or longer. Here's another wave field modeling. This is 2D, and now we're looking at a cross section so you can see it's in depth. We're going to start with no scattering, and then we're going to compare it with scattering. Um, and here you can see we get a nice clean wave field propagating some very clear reflections. All this is pretty much of a simple wave field, which is what you might see in a textbook. There is a lot of energy in the surface waves, but it's slow and it's isolated. Now I'm going to show the wave field modeling with scattering. Now the surface velocity model you see in the lower left, it has layering, and the lower left only goes down to 30 meters, so we're looking at the very near surface. It has layering, but you can see there's some heterogeneities in the top two layers. So now let's run the modeling, and you'll see there's a very significant amount of scattering. And all that energy that was previously in the surface waves is now creating secondary sources, and it's creating a lot of junk energy down deep. And this energy is going down to reflections, and this is the problem noise. So here we compare the wave field snapshots from the two previous simulations. On the top is the wave field without scattering, and you can see we have a nice clear direct P arrival, some clear reflections. And the bottom is with scattering, and now the direct P arrival is very weak, and we have a lot of junk energy after the first arrival. And notice this junk energy is actually also traveling down deep. This will become reflections. There'll be problematic reflections, junk reflections, and that's what I call the coherent noise. You might ask, where did all this junk energy in the bottom simulation come from? Well, it's here in the top simulation. It's in the surface waves, and it's actually dramatically clipped here. But the energy is up there. It's strong. It's slow, so it doesn't affect things as much. But if it leaks out, it causes the problem that you see at the bottom. It's not only heterogeneities that can cause this scattering. Here in the bottom, you can see a surface velocity model with gentle undulations. This is only the top 30 meters or so, and these undulations are actually very realistic. And you'll see that even this causes a lot of scattering. Surface waves are very sensitive to having a perfect one-dimensional model, and variations from one dimension cause this scattering. So this scattering is almost as bad as what we saw before. So in summary, refraction multiples, they start with slow surface S velocities that cause strong P source to S and surface wave conversion. And this happens in the top 10 or 50 meters. And then heterogeneities in the near surface cause strong leaking and conversion of surface waves to P noise. And this can be caused by layering, undulations, scattering. And the near surface is messy at scales of 2 to 20 meters. And the wavelengths are that small because the surface S velocities are so short or so low. Much of this P noise is actually corrupted reflections and refractions, and that makes it very coherent noise. So very little energy remains as primary P reflection energy. So the ratio of primary P reflection energy to coherent noise can be very low. Can be 10% or can be 0.1 or maybe even less. And then you have a multiplicative effect at the source and the receiver. So if you have 10% remaining at the source and 10% at the receiver, that means your net result is only 1% remaining. And this is why we sometimes need 10,000-fold with land seismic data. So let me especially hit home the problem with this coherent P noise. That's effectively corrupted reflections. So I'm going to do synthetic modeling and create this elastic shot gather that you see here. And this is using the velocity model that you see down here. This is the top 30 meters. I showed you this before. And you can see we've created a pretty realistic data set. Weak surface waves, S refractions, and P refractions. Now, the model has a booming reflector at the bottom. It's down here. And actually, this is incorrectly positioned. Okay, so now that shot gather in the previous slide that I showed you, that's the left one here. And what I'm going to do is redo the modeling, and I'm doing here using the Carl Rigoni trick. So what he did, and what I'm doing here, is we redo the modeling using only the top 200 meters of the near surface. So this contains no reflections. It only contains surface traveling energy. And since this is synthetic data, we can subtract the two, and the subtraction is perfect. And the result you see here, which appears to contain only reflections, and it does contain only reflections, but a lot of this is corrupted reflections from the junk energy. So what I'm going to do is apply statics to this, which works well, and then perform pre-stack time migration. And the result is here. Now the correct image is, I think you can see some of the trapezoids here that you expect. And if you look carefully here, you can also see trapezoids oriented in the different directions. They're faint. If you do only acoustic modeling, they actually come out beautifully. But you see there's a lot of, noise that corrupts the image and actually swamps the signal. And here's the booming bottom of model reflection. And it comes out sort of okay. But so even though in this case, using the Carl Rigoni trick, we get a very noisy result. That shows you the strength of all those junk reflections, which are a big problem. And the problem is here, these junk energy that occurs after the first arrival. The fraction of energy that's direct P arrival is actually very low. So what can be done? And there are some things that can be done. We can improve downward traveling energy at the source, and we can improve receiver sensitivity to downward traveling energy. And these improvements might be mild, but if you do 2 or 3x improvement at the source and the receiver, that helps a lot. That'll correspond to 4 to 9 times improvement. And this can be done in the field, and it can also be done in processing. It can be done virtually using digital arrays. Now, more data density in the cross-line direction also helps, but it helps only marginally, and it can be expensive. So let me show you some examples of using this array trick, digital array trick, to improve the downward traveling energy. So here I have data. This is from the Netherlands scan data. It's a publicly available data set. And the nice thing is it had receiver spacing of 5 meters. So I could dynamically create arrays. On the left, we have a point receiver. In the middle, what I've done is I've taken 6 of those receivers and just done a straight sum as the old analog arrays would be. And you can see we've significantly improved the signal noise quality, but the refraction multiples are strong. What I've done in the third slide is I've created optimized phased array to focus on downward going energy. This is like a steering done in optimized phased radar. In astronomy, they also call it adaptive optics. But so if you had a perfectly one-dimensional Earth, then just a straight sum would be the proper way to focus downward going energy. But with a heterogeneous Earth, you have to be smarter and do corrections at each receiver. And that's where a digital array comes in. So we can do those corrections and focus the array more on downward going energy. And you can see now the reflections are clearer in the red circles. In the next slide, I'm going to look at the right 2 data displays. So here they are again, and then I'm going to show you the difference on the right side. I compute the difference, and you can see in the difference we've removed a lot of these refraction multiples, and the reflections are now clearer here and here. Here's a stack comparison. On the left is the image with just radon, and you can see what happens. You get a no data zone. But on the right, we've done the optimized phased array, and you can now see some images here. This is still somewhat subtle, but we combine this with statistical signal enhancement. And we've tried to create or bring out the signal in these no data zones, and we haven't had much success. But with the optimized phased array, you can now see we get some very reasonable signal coming through in these previously no data zones here. So this shows promise. And you can also do the same thing at the sources. So in summary, refraction multiples are a big problem. They're strong and they're difficult to remove. There's not much understanding about them. And they are a complex process. They're caused by a combination of P source converted to S and surface waves, and then converted again back to P noise. You might think this double conversion is, won't be that strong, but each one of these conversions is 90 to 95%. So the remaining energy is the remaining noise energy is pretty strong. And the problem is this produces very coherent noise, effectively corrupted reflections. And we have few tools to really address this, and radon is not so good. But understanding them points to ways to deal with them in acquisition and processing. And that's to improve the downward energy propagation and have less energy conversion in the near surface. And I think this will lead to more efficient acquisition and better quality data. Thank you very much.